Welcome back. Now that we have gone over derivation of some of the solutions to different boundary conditions, today we will go over a couple of numerical problems. The first one deals with carburizing of steels and evaluating the case depths or carburizing time required, and the second one deals with evolution of concentration profiles in a multi-component diffusion couple. So, here is the first problem. This is on the carburizing. A thick steel part with initial carbon content of 0.18 weight% was exposed to a carburizing atmosphere at 820 degree centigrade with constant surface concentration of carbon at 0.8 weight%. So, the original carbon content of steel is C naught equal to 0.18 weight% and the constant surface concentration maintained during carburizing is C s equal to 0.8 weight%. Assume that molar volume and interdiffusivities are independent of composition. Interdiffusivity of carbon in steel should be considered here, and since the interdiffusivity can be assumed constant, we can use the solution that we have derived for the carburizing boundary conditions, that is the semi infinite boundary conditions. And since the problem states that the steel part is thick, which means it obeys the semi infinite boundary conditions. So, if we can draw the schematic of the steel part, carburizing surface on this side left, let us call this as x equal to 0, and it is thick enough so that the carbon does not diffuse all the way to the other side. So, the other surface can be considered as x equal to infinity. The concentration on the surface is C s, which is 0.8 weight%, and the original concentration is maintained at all times at the other end, which is C naught, and at any time t we have seen the diffusion profile will be something like this. Now, the first problem is, if the case depth of the carburized steel is taken as the depth at which carbon concentration drops to 0.4 weight%, determine the time required for achieving a case depth of 0.8 mm. So, we want to find the time at which at x equal to 0.8 mm, this is the x, 0.8 mm is 800 micron. The carbon concentration achieved, let us call it C x, is 0.4 weight%. So, we can use the solution that we have derived, which states that C x minus C naught divided by C s minus C naught is equal to 1 minus error function x over 2 root dt. Now, we are considering the ratios here, and since the problem states that the molar volume can be assumed constant, so it should not matter which unit we are using. So, we can straight away use the weight% as given, and on the right hand side we need to evaluate this error function term, which contains error function of x over 2 root dt. X is given here, which is 800 micron, and d we need to consider the interdiffusivity of carbon in steel. Now, in the given table we see there are two phases, austenite and ferrite, and the activation energy and frequency factor for carbon diffusion are given. Now, which one we should use? since the temperature being considered is at 20 degree centigrade, which is 1093 Kelvin. At this temperature, the stable phase in this low carbon steel should be austenite. So, we should use diffusivity of carbon in austenite phase. So, if we evaluate D equal to D0 exponential minus Q by RT. So, we can write D0 for austenite is 1 times 10 to the power minus 5 times exponential. Q is 136,000 joules per mole minus 136,000 divided by the gas constant R is 8.314 times temperature is 1093, and so we get D equal to 3.2 times 10 to the power minus 12 meter square per second. Since we are considering the distance scale in microns, let us convert this to micron square per second. 10 to the power minus 6 meters is 1 micron. So, 10 to the power minus 12 meter square is 1 micron square. So, the diffusivity is 3.2 micron square per second. So, let us refer to this error function table in a moment. So, now we need to substitute and find out. So, we know C naught, Cs and Cx, and Cx is 0.4. So, we can write 0.4 minus 0.18 divided by 0.8 minus 0.18 is equal to 1 minus error function x is 800 micron divided by 2 root d in micron square per second, which we evaluated as 3.2 times. We need to find the carburizing time. Okay. So, we can solve this. So, let us call this quantity inside error function as z. So, error function z equal to, from this equation we get error function z is equal to 0.64516. So, we need to evaluate first value of z, which will give error function z equal to 0.64516. So, we can refer to the standard error function tables which are available. So, this is error function table. The way we read this is, on the leftmost column you have the values of z up to 1 decimal place, and on the right side, these are on the topmost row are the values of z in the second decimal place. Right. So, if we want the error function of 0.32, we refer to 0.3 and the second decimal place is 2. So, 0.32, the error function 0.32 is 0.34913. Okay. Now, we need to find out z such that error function z is equal to 0.64516. Now, exactly this value may not appear in the table, but we can assume the linear relation within the small range of z. Okay. So, let us see one value which comes before 0.64516 and the other which is slightly greater than 0.64516. From this table, we have 64203 and 64938. This corresponds to 0.65 and 0.66. So, you can see error function 0.65 is equal to 0.64203 and we need to evaluate error function z, which is 0.64516, and error function 0.66 is equal to 0.64938. So, if we assume linear relation, we can find the value of z here. So, we can write z minus 0.65 divided by 0.66 minus 0.65 is equal to 0.64938 0.64516 minus 0.64203 divided by 0.64938 minus 0.64203. This will give me the value of Z as 0.65426. So, if I substitute for Z, which is 800 divided by 2 root 3.2 t is equal to 0.65426, this will give me the value of t, which comes out to be 11,685 divided by 3600. This will come out to be 30.4 hours. So, in this particular case, to achieve the case depth of 800 micron, the carburizing time should be 32.4 hours at 820 degrees Celsius, and the case depth in this case is defined as the depth at which carbon concentration becomes 0.4 weight%. Now, the second part of the problem, what will be the case depth if carburizing time is doubled? Now, this is simple. Once we know one carburizing time for one case depth, we can straight away use the Boltzmann parameter, right. As you see this equation here, C is a function of x over root t, right. Everything else is constant, including d, C naught, C s. So, C x is a function of x by root t, which means, so for part B, we know C x is a function of x over root t, which means x 1 by root t 1 is equal to x 2 by root t 2. So, if you want x 2, that should be equal to x 1 times root t 2 by t 1, and the problem says the carburizing time is doubled. So, t 2 by t 1 is 2. So, this becomes root 2 times x 1, which suggests that if we double the carburizing time, the case depth should become root 2 times the original one. So, x 2 is straight away root 2 times the initial case depth is 0.8 mm, this is in mm. So, x 2 comes out to be 1.13 mm. Okay. So, this is how we can determine carburizing time for the given conditions or carburizing time for the given case depth, or we can determine what should be the case depth in given carburizing time at the given temperature. Okay. So, let us move on to the second problem today. This problem is calculating the concentration at given x and t in a multi-component diffusion couple. Okay. Again, we will assume constant interdiffusivity matrix and we will consider a ternary diffusion couple example. So, this will give you an idea about how to use the multi-component diffusion equation to actually calculate the concentrations at various x and t in an infinite diffusion couple. We will solve this for ternary, but equally applicable, it will be equally applicable for quaternary or higher order system, and we will be using the analytical solutions for constant interdiffusivity matrix. Okay. So, the problem says a solid-solid infinite diffusion couple was assembled between two terminal alloys whose compositions are given in the table below, right. So, we have a diffusion couple So, this is the initial interface between two terminal alloy, let us call it x equal to 0, and this is an infinite diffusion couple. So, the leftmost terminal is minus infinity, rightmost terminal is plus infinity. Again this means that the diffusing species do not penetrate by diffusion all the way to the terminal ends, so that the infinite boundary conditions are maintained. Now, in the left terminal alloy, the initial concentrations, which we typically denote by C minus. So, C 1 minus is 0.1, let us write in terms of mole fractions. C 2 minus is 0.42, and C 3 minus is 0.48. C 1 plus is 0, this is let us call 0, C 1 plus equal to 0, C 2 plus is 42. So, C 2 composition is same in both the terminal alloys to start with, and C 3 plus is 0.58. So, this is the initial concentration profile. You can see it is a step function, there is a discontinuity at x equal to 0, except for C 2, because in this case C 2 is constant on both sides. The couple was isothermally annealed for 48 hours. So, the diffusion annealing time T is equal to 48 hours. If we convert it to second, because we use diffusivities in meter square per second or micron square per second. So, it will be 172,800 second. What should be the composition of the plane located at minus 700 micron in the diffusion zone? So, minus 700 means it will be on the left side. So, x is equal to minus 700 micron. Assume that the molar volume and interdiffusivity metrics are independent of composition, and the interdiffusivity matrix is given here. These are the ternary interdiffusion coefficients. So, we need 4 interdiffusion coefficients, since there are 2 independent components. D11 tilde 3 is 4.5 micron square per second, D12 tilde is 0.3 micron square per second, D21 tilde 3 is minus 4 micron square per second, and D22 tilde 3 is 1.7 micron square per second. Now, we can use the multi-component diffusion solution in order to obtain the concentrations at the given x and t. As we have derived the solution, this is in the matrix form, and we can write C at x and t, where C is a column matrix. Since there are 2 independent concentrations, it is a 2 by 1 column matrix. So, it will contain the term C 1 and C 2, since we have interdiffusivities with component 3 as dependent, right. The superscript denotes the dependent component. This should be 1/2 I minus P times ERF times P inverse C minus. C minus is the column matrix of independent concentrations in the left terminal alloys. So, this will be C minus would be 0.1 and 0.42 plus this should be 1/2 I plus P times ERF times P inverse times C plus. C plus is the column matrix of independent concentrations in the right terminal alloy. So, this should be C 1 plus C 2 plus, which is 0 and 0.42. Now, we know what are these matrices P, ERF and P inverse, right. ERF is essentially a diagonal matrix containing error function terms, right, and these error function terms are in terms of the eigen values of the diffusivity matrix. So, if we write ERF, it looks like error function x over 2 root d1t. This is a 2 by 2 diagonal matrix. So, the non-diagonal elements are 0. The second term is x over 2 root d2t. d1, d2 are the eigenvalues of d tilde, and P is a matrix formed by eigenvectors of d tilde, and the eigenvectors are arranged column by column. Since d tilde is a 2 by 2 matrix, so there are 2 eigenvectors. So, the P is again a 2 by 2 matrix. So, now we first need to find out the eigenvalues and eigenvectors of d tilde, right. So, this is a little bit of revision of lot of mathematical concepts. We already gone over some of those, like Laplace transforms, and this is again a good example. You will get an opportunity to revise your matrix algebra concepts, right. So, that is why I am going over these problems. So, to evaluate the eigenvalues and eigenvectors of d tilde, right, we write the typical equation d tilde times x is equal to lambda times x. So, this will give me d tilde minus lambda I times x equal to 0, where I is a identity matrix. For 2 by 2 identity matrix, it will be 1 0 0 1. Okay. So, obviously, x equal to 0 is a trivial solution. So, we need d tilde minus lambda I equal to 0. So, if we evaluate the d tilde minus lambda I matrix, since I is an identity matrix, lambda I would be again a diagonal matrix with both the diagonal terms being lambda and the non-diagonal terms being 0. So, if we subtract lambda I minus d tilde, we should get (4.5) minus lambda. The non-diagonal terms will remain as it is, and the diagonal terms will subtract lambda from them. So, now we need to evaluate lambda by putting determinant of d tilde minus lambda equal to 0. So, if we evaluate the determinant of this matrix, it will be 4.5 minus lambda times 1.7 minus lambda minus, and there is a minus sign again here. So, this should be plus 4 times 0.3. So, we will get a quadratic equation in the form lambda square minus 6.2 lambda plus 8.85 should be equal to 0, and the roots of this equation would be lambda equal to minus b plus minus square root of b square minus 4ac divided by 2a, and in this case a is equal to 1, b is minus 6.2 and c is 8.85. So, if we substitute, we will get 2 roots, lambda 1 equal to 3.9718 and lambda 2 equal to 2.2282. So, these are the 2 eigenvalues. In our terminology, these are d1 and d2. So, lambda 1 is d1, lambda 2 is d2. Now, we need to find the eigenvectors. to find the eigenvectors, we substitute each value of lambda one by one back into this solution. D tilde minus lambda I is x equal to 0. So, first for lambda 1 is equal to 3.9718, we substitute, we get 4.5 minus 3.9718, 0.3 minus 4, 1.7 minus 3.9718 times x, we can write as their elements as x1 and x2 should be equal to 0, 0. We will get two equations, we can solve any one of them. So, we get 0.5282 x1 plus 0.3 x2 equal to 0. The second one basically will get the same equation. So, we have two unknowns, but only one equation. So, we can fix one value and get the other one. This indicates why we take the matrix P with diagonal elements being 1. So, it is easier to do the calculations. So, here if we, this is the first eigenvector. So, if we assume the first element x1 to be 1, we can find x2 which comes out to be minus 0.5282 divided by 0.3, it should be minus 1.7607. Similarly, we can do for lambda 2, which is equal to 2.2282. If we substitute 4.5 minus 2.2282, 0.3 minus 4, 1.7 minus 0.2282 times x1 x2 equal to 0, 0. So, we get an equation of the form 2.2718 x1 plus 0.3 x2 equal to 0. For the second eigenvector, we take x2 as 1. So, x2 equal to 1, x1 should be minus 0.3 divided by 2.2718. So, x1 comes out to be minus 0.1321. So, we have obtained our matrix P here. So, P comes out to be, we arrange the eigenvectors column by column. So, the first eigenvector is 1 minus 1.7607, second one is minus 0.1321 and 1. Now, next we need to find the inverse of P. So, to find the inverse of P, we can use the formula. We have to first find cofactor matrix of P and take its transpose and divide it by the determinant of P. Okay. So, let us see the cofactor matrix of P. For a 2 by 2 matrix, it is easy. We just switch the positions of diagonal elements among themselves and the non-diagonal elements among themselves and multiply the non-diagonals by minus 1. Right. Here the diagonal elements are same, so they will remain same, and this becomes 1.7607, this becomes 0.1321 and 1. and we take its transpose. So, the cofactor matrix of P, and we have to take its transpose, which means we arrange rows as columns or columns as rows. So, this comes out to be 1.7607, 0.1321 and 1, and we need determinant of P. This should be equal to 1 times 1 minus the product of the other two, minus minus becomes plus. So, this will be 1 minus 0.1321 times 1.7607, which comes out to be 0.7674. To find P inverse, we divide the transpose of cofactor of P by the determinant of P, and so we get P inverse. So, let us write here P inverse we have obtained as 1.3031, 0.1721, 2.2944, 1.3031. So, we need to find the error function terms. So, the first error function term is x over 2 root d1 t, and x is given to be minus 700 micron divided by 2. d1 we have obtained as 3.978, that is the first eigenvalue, 3.9718 times the time is 172800 seconds. Now, we can refer back to the same error function tables and we can evaluate the error function of this term. Now, the most error function tables will give you error function z for only the positive values of z, but we know error function minus z is equal to minus error function z. So, it is easy to refer to those tables and get the values of error functions of negative values. So, this comes out to be minus 0.44278. The second error function term is error function x over 2 root d2 t, d2 is the second eigenvalue. So, we can write minus 700 divided by 2 square root of 2.2282 times 172800. Again, referring back to the error function table, we will find the error function of this to be minus 0.57494, and so our matrix ERF comes out to be minus 0.44278 0 minus 0.57494. Now, referring back to the solution, we need this product P times ERF times P inverse. Okay. So, we can obtain this product P times ERF times P inverse is equal to, substitute for P, which is 1 minus 1.7607 minus 0.1321 1 times minus 0.44278 0 minus 0.57494 is 1.3031, 0.1721, 2.2944, 1.3031. So, we can take the product of first two and then again take the next product. If you solve this, we will get P times ERF times P inverse, a 2 by 2 matrix. of minus 0.4120, 0.0215, minus 0.2871, minus 0.6129. Now we have to substitute back in the solution, right. So we are using this solution here. Now we know I is the identity matrix 2 by 2 here. We know this P ARF times P inverse, and we know C minus and C plus. Okay. So we substitute in them and find C of x t. X specifically here is minus 700 micron and t was 48 hours, will come out to be, again it is a column matrix, concentration matrix 0.0706 and 0.4344. So what it tells me, at x equal to minus 700 micron, after 48 hours of diffusion annealing, the composition plane that will be developed is C1 equal to 0.0706, C2 is equal to 0.4344, and C3 will be just 1 minus C1 minus C2, which comes out to be 0.4950. So this will be in atom fraction. Okay. So this is how we can use the multi-component diffusion solution to get the concentration as a function of x and t in any multi-component diffusion couple. Again, we illustrated this with a ternary diffusion couple, but similar procedure you can apply to quaternary, quinary or higher order diffusion couples. Okay. We assumed the interdiffusivity matrix is constant throughout the diffusion zone, and also molar volume was assumed constant. So we can use, instead of moles per centimeter cube, we can also use the atom fraction or even weight fraction, because molar volume is constant, it is independent of composition. Okay. So with that we will stop here for today. Thank you.